In this situation, we're going to look at the basketball scholarships offered by colleges for those players that are over 6 foot tall as opposed to those that are not. In this problem, a sample of 50 colleges randomly selected, and they figured out the average number of scholarships for those over 6 foot tall and those that were not. So in this particular case, they're looking at the idea that the average number of scholarships is greater for the 6 foot tall players. So go ahead and set up your null and your alternative. Hopefully this is what you got. Hopefully you remember that you have to mark this down every single time so the person knows what you're talking about here. So now you're going to make a decision. This is a one-sided test. Is it a z-test or is it a t-test? And then I want you to go ahead and mark all your information down, or at least organize all your information in some way. Pause the video, go ahead and do that. Hopefully you decided this was a one-sided test and you got positive 1.28 as your critical value. Well, now if we're going to use this information and we're going to test the idea that these are equal or over 6 foot tires get more scholarships, now we need to go ahead and find our test statistic. Go and plug everything in and go ahead and get that number. Pause the video and come back when you're ready. So plugging everything in and then go ahead and grab your calculator, you end up with a test statistic of positive 1.06. Well, in this case, think about where that falls and then decide are you going to reject or fail to reject. Again, pause the video. Once you make a decision, come back and see if you agree. Well, in this case, the 1.06 is clearly in my non-critical region, in my non-shaded region, so it means we fail to reject the null hypothesis. Keep in mind, just like the past chapter, this doesn't mean that the two are the same. This doesn't mean that the shorter players and the taller players get the same number of scholarships. All it means is there's not enough evidence. Doesn't mean they won't go out and do another study and find something different, but in this case, there's not enough evidence to support that idea. Now we're going to turn our focus to two populations. We've been looking at one population and a claim made about one area or one thing or one set of subjects. Now we're going to look at the averages between two populations. The key right now is that these two populations are going to have to be independent of each other. If they're dependent, we'll look at that at a different time. But in this situation, let's say we're looking at the average house value in one town as opposed to the average house value in another. Or the salary in one time period versus the salary in a different time period. And we're trying to figure out, is there a significant difference, increase, decrease, whatever the situation poses. Well, how are we going to set up our hypothesis? They're really not going to be any different than when we did when it was a one sample. We're still going to focus on the equal sign for the null, and we're still going to focus on the inequalities that do not include the equal sign for the alternate. The only difference between this is, instead of it being mu on one side or p on one side and a number on the other, there's going to be mu's or p's on both sides. The key to a situation like this, we need to mark down what our populations are. So let's go back to one of the examples we talked about, and let's talk about the average house value in two towns. Well, let's say we want our first town to be Medford, and we want our second town to be Tabernacle. It's important that we go ahead and write this information down, because when I go through and I get all my information and I put down my X bars and my sigmas, I need to make sure that the person who's reading this data, or myself later, knows where all the information came from, because it's going to be very important, because that could change my alternate hypothesis. The fact is, these two symbols are going to be very similar to each other, and they're going to end up being opposites if you just simply flip-flop these two things. So you need to be very careful with what you do. When you go through this, we're going to have to decide, is it a z-test or is it a t-test? And nothing's going to change from what we did before. Check your sample sizes. Are they 30 or above? If they are, it's a z-test. If they're not, look at your standard deviation. Is it from the population? If it is from the population for both of them, then you go z-test. If your samples are, either one is small. If one's big and one's small, you have to go t. Or if you're dealing with unknown standard deviations, which is typical, we're going to have our two formulas. So I'm going to go ahead and write those on here. Well, here's the formula. And go ahead and pause the video and write that down for yourself. But the question you're probably asking yourself is, well, is that a Z or is that a T? In this case, the best part about this is nothing actually matters. They're both going to be the exact same formula. So when you find your test statistic, you're going to do the exact same thing. You're going to take your two X bar values, your two sample means, you're going to subtract them. Then you're going to take your standard deviations. But notice that I have a square up here. So when I go ahead and I looked at this, I squared both of my standard deviations. That's because we can't add standard deviations together. You can add variances. Think about the idea of the Pythagorean theorem, and that's kind of what we're doing here. Well, if you think about our standard formula before, we just did this. That was my denominator. That was my standard error. If I take that value and I square it, it's going to give me this. And that's called my variance. We've talked about that before. That's basically what this is. I have my variances. When I add my two variances together, I'm able to do that in statistics. But then I want a deviation. That's why I have to take the square root. This is going to give me my test statistic. In Z or t-test, this is going to be the same idea. The only difference is now, do I go t-test or do I go Z? If you're talking Z, you're going to go inverse norm in your calculator, deciding if it's a one or a two-sided test. If it's a T, you're going to go inverse T. The only thing you have to worry about here is when you go Z-test, it's identical. Nothing changes. When you're talking T, you're going to need that degrees of freedom. Now, there is a fancy formula to get this, but very simply stated, take your N1, subtract 1. Take your N2, subtract 1. Whichever of these is smaller. So you want the smaller of the two, because we're going to err on the side of caution. And when you go smaller, that's going to put us with a little bit more region outside, a little more bubble on the outside. So it's going to give us a very different value. Even if the sample sizes are very close, always err on the side of caution here and take the smaller of the two sample sizes, which is going to give us a larger critical value. So this is the setup for this. Now look at a couple examples.